Before we go for the IP addresses and how they are assigned, I just want to give you an introduction to the computer structure and architecture. Computers or all the electronic devices are made of a component which is called a transistor. A transistor has three terminals: gate, drain, and source. The I of G, or the current of gate, would always be equal to 0. But it actually acts more like a control unit. When we apply a voltage to the gate which is bigger than the source by a special amount which is called the V of threshold, then we would have a current. So if V of gate source, when we say VGS, we mean the V of gate minus the V of source. So when we apply a voltage to the gate which is bigger than the source by an amount which is called V of threshold and is only dependent on the structural parameters of transistor, we would have a current, or I of D, which would flow through the drain to source and is equal to 1/2 mu n WL C oxide V of gate source minus V of threshold square. The first term in here is only dependent on the structural parameter of the transistor and doesn't vary. But as you see, the more voltage we have to gate source, the more I of D we have. So in summary, we could say that if V of gate source is bigger than V of threshold, the transistor would act as just a wire or short circuit, that a current is flowing through that or is passing through that and is completely dependent on the V of gate source. On the other hand, if V of gate source is smaller than V of threshold, then the current would be 0, and we could say that the transistor is off or acting as a open circuit. So what we could say is that the transistor would act as a switch. It has two states. One of them is if V of gate source is bigger than V of threshold, and the transistor would act as a wire or short circuit, and the other one is when the V of gate source is smaller than V of threshold and the transistor would be off or open circuit. So we have two states. One of them is on and the other is off, using one transistor or one switch. But now let's say that we have two transistors. Well, we would have four different states. Either they are both off, or the first one is off, the second is on, or the first is on, the second is off, or they are both on. So using two transistors, and by getting the access to the gate terminal in here as a control unit, we could create four different states, as you see in here. But working with on and off is a little hard. So instead, we call by convention, we say that off is equivalent to 0 and on is equivalent to 1. So because we only have two numbers, we call it a binary, and every 1 or 0 would be a binary digit, or we could just get the B in the first term and IT in the second term and call it a bit. So 0 or 1 is just a bit, each one of them, but we know that it is actually a transistor that should be on or off, nothing more. And this being on and off is controlled by us by applying a voltage to the gate of these switches. So in this case, we could say that off and off is equivalent to 0, 0, off and on is equivalent to 0, 1, on and off is equivalent to 1, 0, and if they are both on, we could say that it is equivalent to 1, 1. You see, we call on a 1 and off 0. But you could just replace other numbers. For example, you could say that off is equivalent to 2.4 and on is equivalent to 100.1. It doesn't matter. We have only two states, but because it was easier, we called them 0 or 1. So in decimal, we could say that 0, 0 is the first state, so it is 0. 0, 1 is 1, 1, 0 is 2, and 1, 1 is 3. As you saw, we have four different states. Using two switches, we have four different states. You could just prove that if we have three states, three switches, we could create 2 to the power of 3, which would be equivalent to 8 different states. Or 4 different switches, we could have 16 different states.